Hello everyone, myself Srivalli, working as an assistant professor in the Department of Cybersecurity and Data Science in MLR Institute of Technology. So today, the overview of presentation includes what is connectivity, what is cut vertex, cut edge and cut set, and also we are going to discuss about edge connectivity and vertex connectivity. So here, first let us understand what is meant by a connectivity. So this connectivity, it is a branch of mathematics. So where we can say that if it have any path from one vertex to another vertex, then it is a connectivity. Or otherwise, if you don't have any connectivity, then we can say it is a disconnected graph. So this connectivity also, it works on the main principle that is based on the connected graph and disconnected graph. So a graph is said to be connected if there is a path between every pair of vertex. So as we have seen in the last sessions also about connected graph and disconnected graph in types of graph session. So connected graph is nothing but, so if you have a path between every pair of vertex, means let us suppose I have one graph, so where I have multiple number of vertices like from V1 to Vn, and I have number of edges also. But if I want to travel from the vertex V1 to Vn, if we have a path between every pair of vertex, then I can say that it is called connected graph. So even if one pair of vertex path is disconnected, then I can say that it is not a connected graph, it is called disconnected graph. So that is what here we have. A graph is said to be connected if there is a path between every pair of vertex. So whatever the vertices we have from V1 to V1, for every pair means V1, V2, V3, V4, V5, V5, V6 or V8, V9 or V10, Vn also, means like that if you consider any pair of vertices, you should have some path between every pair of vertices. Then only I can say that is called connected graph. So from every vertex to any other vertex, there should be some path to traverse. So traverse is nothing but visiting the nodes here. So if you want to traverse from the vertex 1 to another vertex 2, so I can say that there should be some path here. Without path, I cannot able to traverse from one vertex to another vertex. So this particular connectivity, we can say that it is called connectivity of a graph. A graph with multiple disconnected vertices. Not only disconnected vertices means only one, multiple disconnected vertices. So which is nothing but V1 to V5 is disconnected, V7 to V9 is disconnected. Like that, if I have multiple number of disconnected vertices and edges also, then I can say it is called disconnected graph. So here we have in this connectivity concept, we have two types. One is edge connectivity and the other one is vertex connectivity. So before going to discuss about edge connectivity and vertex connectivity, first of all you need to understand three types of terminologies for the connectivity, that is cut vertex, cut set, cut edge. So first let us learn all the three, then we can go for edge connectivity and vertex connectivity. So in the above connected graph, one can traverse from A to vertex E using the path here. So just see here, I have taken one figure and I have taken one graph. We can also call it as graph here. And let us suppose here two graphs I have. Let us suppose this is G1 and this is G2. Now in the G1 I have the vertices like A, B, C. In the G2 I have D, E, F. Now what they are saying is one can traverse from A to vertex E. What is vertex? Where is vertex A in the graph 1? And one can traverse from the vertex A to a vertex E. But how it is possible? This vertex A is in G1 and this vertex E is in G2. But if I have path from C to F, so if I have path from here, then I can able to traverse. So what they are saying is one can traverse from the path A to vertex A using the path A, B, E. So here A, D, E or A, B, E. In the following example, traversing from vertex A to F. So traversing from the vertex A to F here. So it is not possible. Why? Because A to F is nothing but what here? Like this direct connection here. So it is not possible. So it is not, because there is no path between them directly or indirectly, hence it is a disconnected graph. Why? Because I don't have any path to traverse from here to here. So this is G1 and this G2. So as I don't have any path from G1 to G2, then I can say this is called disconnected graph. So then first let us understand what is meant by cut vertex and cut set cut edge. So first let us see here what is cut vertex. Let capital G be a connected graph. A vertex V belongs to G. So here what is meant by G? Capital G. So which is nothing but I am considering this one as assuming this one as connected graph. So connected graph means where we have path between every pair of vertices. So let us suppose this is a cut vertex. Let us suppose this is a connected graph G. And a vertex V means whatever the vertices we have here in this connected graph, I am just denoting with V. So a vertex V belongs to G, and that vertex we can say that it is called a cut vertex if deletion of that V from the total graph also it results into disconnected graph. So here try to understand here. So let us suppose this is the original graph where I am representing with the original graph name is symbolically, so with letters capital G, and whatever the vertices we have here, those vertices I am denoting with V altogether, whatever it may be, A, B, C, D, E, F, G, H. So whatever it may be, I am denoting with V, and this vertex belongs to G only. And if deletion of that V, so if deletion of that V means what? That V can be anything. So why? Because all the vertices I am denoting with V. If the deletion of any vertex A, B, C, D, F, G, H, any one vertex, if I am going to delete from this connected graph, and this particular graph is going to be disconnected, means because of removing that particular vertex, I cannot able to traverse from one vertex to another vertex. Then I can able to say that it is called disconnected graph. So let us suppose here what I am doing is, this is original graph and here I am removing C. So if I remove C here, how it can be is, so the original graph only I am removing C. If the vertex is removed, obviously the edges also will be removed which are attaching to that vertex. Then A to B, B to D, so that's it. So I cannot take D to C or B to C. Why? Because C I am removing the vertex. And even C to E also I am removing. Then F, G, E, F, G, H. So this is A, B, D, E, F, G, H. This is what, this is the second figure here I have written. So now if you observe, because of this deletion of one vertex, I can able to make this graph as disconnected. Why? Because if I want to travel from the source A to destination H, how can I able to travel? A to B, and here I should have some connectivity, but I don't have any connectivity. So from this to E to H it is possible, but I have removed the vertex. Since I have removed the vertex C, I don't have any path from vertex A to H. And as even if I go from A to D, so here also I don't have any path. Even if I go from A to B, B to D, again D to C only it is there. But C to D I don't have any connectivity. So because of this deletion of the vertex C, I can able to make this graph into disconnected. That's why it is called cut vertex. C is called, means because of the vertex C deletion only you are going to disconnect. So means this is called cut vertex. So like this you can have many number of cut vertices in the graph. So like this I have taken B also. So what is B? Vertex B is also cut vertex. How I can say this cut vertex B here is, so here what I am doing, only vertex A, the B vertex which are attaching to any vertices I am removing. So only A you will get, D to E, D to C, C to E, E to F, F to G, G to H, H to E. So now this is a, we can say that this is also called disconnected graph here. So and even E vertex, if you remove E also, just like C, similarly for E also if you remove, so like this, just opposite to this one you will have. So this is called cut vertex. Now similarly, just like cut vertex, we also have cut edge. So what is cut edge is, let G be a connected graph. An edge of E belongs to G is called cut edge of G if deletion of E from G results in disconnected graph. So in the previous one, cut vertex, the deletion of vertex, if you are making it to disconnected, it is called cut vertex. If the deletion of edge only, if you are making it into disconnected graph, that is called cut edge. So let G be a connected graph. An edge E belongs to G is called cut edge of G if deletion of E from G results in a disconnected graph. So let us consider here. So let us suppose here I have one figure where I have A, B, C, D. Again C to E, E to F, F to G, G to H, H to E. So like this, if you have here, let capital G be a connected graph. Here I am representing the total graph as with G, where it is called connected graph. So connected graph means every pair of vertices will have the connectivity. So A to B, and if I take A to C also I have connectivity. If I go for A to D also I have the connectivity here. If I want to move from A to H also I have the connectivity like this in whichever path it may be. So now let G be a connected graph. An edge E belongs to G is called cut edge. So how you can say that the particular edge is called connected cut edge here? If deletion of that particular edge is results to a disconnected graph. So here, so let us suppose what I am doing is I am removing this particular edge CE. So if I remove this edge, how it will be? A to B, B to D. So and D to E. So B to C also there. A, D, B, C. Now here again E to F, E to H, H to G, G to F, F, G, H, E. Now I am just removing this particular edge C to E. So because of this I can make this total graph into disconnected graph. I can make this connected graph into disconnected graph. So that's why the C comma E is called cut edge. The same graph here. So in the first one I am just deleting the vertices where I can make this graph into disconnected, and those vertices we can say that cut vertices. And in the second one where I am considering only edges here, with the removal of one particular edge, if I can make this graph into disconnected, that is called cut edge. Next we also have cut set. So what is meant by this cut set here is, if deleting certain number of edges from a graph makes it disconnected, then those deleted edges are called cut set of the graph. So if deleting certain number of edges, so which is nothing but not only one particular edge. So if I remove only one edge, if I can make this, that is called cut edge. But like that, if I able to remove some pair of edges where I can make that particular graph into disconnected, that is called the pair of vertices or edges, we can say that cut set. So deleting certain number of edges. So means it's not possible for some graphs. It's not possible to remove only one edge where it will make it disconnected. So with the possible of removal of multiple number of edges, some set of edges, if I can make the total graph into disconnected, that is called cut set. So if you observe here, this is a figure here. So where I have some vertices like A, B, C, D, and I also have some edges like here. How many edges we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Total 9 edges I have. Now by using this here, the cut set here is E1, E3, E5, E8. How we can say that E1, E3, E5, E8 are cut set here? Let us suppose I want to make this graph into disconnected so that I can count those vertices, set of vertices, and those vertices, those edges I can say that cut set. So let us suppose this graph here, how I am making disconnected is, so now here if you observe, this is A, D, C, B. This is somewhat E, F. Let us suppose you take. Now here how many edges I have removed here is one edge, and this is 2, this is 3, and this is 4. So here if you observe, with the combination of this, not only this one, you can with how many edges you are removing here. So only those edges I can say that it is cut set. So in the same way, if I take, So here this one is removed, and this is also removed, this is also removed, and this one removed. So with the combination of these four edges, I can able to make the graph into disconnected. So then those set of edges we can call it as cut set. So in the same way here, so here if you observe here, so this is also here A, D, C, B, E. So as I can able to make this graph here into disconnected, then I can say the particular set of edges, whatever I am going to remove here, those set of edges we can call it as cut set here. So next, as I told you that we have the two types of connectivity like edge connectivity and vertex connectivity. So let us see here what is meant by edge connectivity. So let G be a connected graph. The minimum number of edges whose removal makes G disconnected is called edge connectivity. So notation here, we will always represent this edge connectivity with lambda of G. In other words, the number of edges in a smallest cut set of G is called the edge connectivity of G. If G has cut edge, then lambda of G we can call it as 1. So what is meant by this here is, let us suppose here I can call this original graph as G, which is called connected graph. The minimum number of edges means with the minimal number of edges in a particular graph, if I can make that graph into disconnected. So the minimum number of edges whose removal. So here the minimum number of edges I am going to remove it, and whose removal makes it into disconnected. So that is called edge connectivity, and this edge connectivity we will always represent with lambda of G here. So in other words, the number of edges in a smallest cut set of G. So number of edges in a smallest cut set means what here? So if you have smallest edges, smallest cut set, if you have, that is called edge connectivity. Means here, if you have only cut edge, if G has a cut edge, then lambda of G we can call it as 1. Now let us suppose we have here the graph A, B, C, D, E. Now I can able to make this graph into disconnected with a minimum number of edges. Let us see here. So here this one, and here what I have did is I have removed these two, and here these two I have removed, and here this one. So this one I have removed here, and even this one also removed here, and even here also this one removed, and this one and this one. So here if you observe here, the smallest one is what, two, only two edges. If you remove, then it is making the graph into disconnected. So in the same way we have vertex connectivity also. So let capital G be a connected graph. The minimum number of vertices, just like minimum number of edges, how you are going to delete it, in the same way minimum number of vertices whose removal makes G either disconnected or reduces G into a trivial graph. So what is meant by trivial graph here? So I'll be having only one vertex, but no other edges, but no other vertices. That is called trivial graph. So what I am doing here is, here I have considered one graph here, capital G, which is called connected graph. So minimum number of vertices. Because of that, if I can make the graph into disconnected, that is called vertex connectivity. So here the minimum number of vertices whose removal makes G either disconnected or reduces G into trivial, which is nothing but it is reducing the vertices to 1. So that is called vertex connectivity. So if G has a curved vertex, then we can say how you can represent here as K of G is equal to 2. So here in the same thing here also we have A, B, C, D, E, F, G, H, I, J. Now if I can able to remove the vertex I and J, obviously the graph will be not disconnected. Why? Because so if I remove I, so then it will be like here only A, and here it like this it will be there. And along with this, if I remove C also, then it is possible to make the graph into disconnected. So then only I can say it is called a vertex connectivity. So what we have discussed today in this session is what is meant by connectivity, and what is connected graph and disconnected graph, and what is cut vertex, cut set, and cut edge, where they are the basic terminologies for the connectivity, and the types of the connectivity also we have discussed, like edge connectivity and vertex connectivity. So by this, we'll end the session for today. Thank you.